Okay, in the next video we're going to look at some of the reactions of acids and bases. Okay, so in this video we're going to look at the reaction of some acids and bases, and in particular we're going to look at the reaction of the non-metal oxides, which are acidic, and the metal oxides, which are basic. So a lot of this stuff recaps from what we did earlier in the year. When we did the periodic table topic, we looked at the oxides of non-metals and metals and the properties of those. And then we also need to do structural formula for these molecules here. That builds on what we did in the chemical bonding topic. So that will build, that builds on that. If some of this I seem to be going too quick over, maybe go back and have a look at those videos. So, carbon dioxide is our first one. Has the formula CO2. The structure, carbon has 4 electrons, so it wants to share 4. Oxygen has 6, it wants to share 2 to get to 8 to have a full outer shell. The two regions of electrons push apart, so we get that linear structure. When carbon dioxide reacts with water, it forms an acid, H2CO3, which we know as carbonic acid. Sulfur dioxide has the formula SO2. The structure of this one's a little bit confusing, but basically it's an expansion of the octet one. So again, look back if you're not sure on that. Sulfur is actually able to have more than 8 electrons because it's in the third period. So it's got, remember, the third shell can hold up to 18 electrons. Oxygen still though wants 2, so they form double bonds. You end up with, each line represents 2, 8, 10 electrons around the sulfur. Those electrons at the top here push apart these electron regions here, gives you that V-shaped, and the reaction there is SO2 plus H2O forms H2SO3. That is sulfurous acid. So all of these obviously have hydrogens that they can donate, that's what makes them acidic. The next one is sulfur trioxide, which has this trigonal planar structure. SO3 plus H2O forms sulfuric acid. They actually use this process a lot to make sulfuric acid in industry, because a lot of places they burn things that have sulfur in them. It forms sulfur trioxide. If you bubble it through water, you will form sulfuric acid. And finally, the final one we need to look at is, we'll do red because matches contain phosphorus and they're red. P4H, not P4H10, P4O10. I think I've got that right, yep. We don't need to know the structure for P4O10, that would be quite complex. So what P4O10 reacts with water, and this forms phosphoric acid, which I talked about before. That's the one in Coke, phosphoric acid. And that one takes a little bit of balancing. We need 4 of those, and therefore we have 12, so we need 6 of those. And I think that balances out now. So now let's look at the metal oxides. We have sodium oxide. Obviously this is a metal and a non-metal, so it's ionic. forms a lattice with 2 sodium ions for every oxygen ion. When we react that with water, we will form sodium hydroxide. And I believe in this case we will form 2 sodium hydroxide, and that should balance. When we react potassium oxide with water, same sort of thing for the formula, plus H2O forms 2KOH. And finally, calcium oxide, CaO. Calcium has a 2 plus, oxygen has a 2 minus, so they balance out. CaO plus H2O forms calcium hydroxide. Hydroxide ion only has a 1 minus charge, so we need 2 to balance out the 2 plus of calcium. Then when we come to balance that reaction, 1 calcium, 2 oxygen, 2 oxygen, 2 hydrogen, 2 hydrogen. That's actually balanced. I don't need to do anything more. I will also point out here, just as we can get amphiprotic substances that can act as either an acid or a base, we can also get amphoteric oxides. These can either act as an acid and a base also. These tend to be generally the metalloids. So the metalloids are the ones that live on that boundary between metals and non-metals, and they can either in some cases act as an acid or in some cases act as a base. I don't think we'll do any more detail on those. It's not explicitly in the Year 11 course. I think it does come up in the workbook though, that's why I mention it, and it is something that is a little bit important as we move into Year 12 chemistry. We do come back and visit, so I just want to make you aware of that for now. So let's continue looking at the reactions of acids and bases. Now, there's a lot of similarities in the way that different acids and bases will react. So it won't matter if we add an acid and a metal oxide, it doesn't matter which acid or which metal oxide, they will all follow a similar pattern. If we react an acid with a carbonate, they'll all follow a similar pattern. It doesn't really matter which acid we use or which carbonate we use. So we can actually fairly easily make predictions about the products in these reactions just by knowing this general information, by knowing these general forms these equations take. So if we start here, if we add an acid and a metal oxide, so I will actually write that out again. If we add an acid plus a metal oxide, we will get salt plus water. What do I mean by that's a general equation? Well, we could pick any acid. So let's pick here nitric acid, and we could react that with potassium oxide. That will form potassium nitrate. So a bit like when we did the precipitation reactions, the parts here will combine and we will get water. Got to balance that equation, so 2 potassium here, 1 here, so we put a 2 out there. Now we've got 2 nitrogen, so we need to put a 2 there. Now we've got 2 potassium, 2 nitrogen, 2 potassium, 2 nitrogen. We've got 6, 7 oxygen, 6, 7 oxygen. 2 hydrogen, so that balances. So that shows that reaction between an acid and a metal oxide will always give a salt plus water. We see a very similar thing happen with an acid and a hydroxide, which is what we would usually call a neutralization reaction. So if we have acid plus metal hydroxide, that will also form salt plus water. So here we'll pick a different acid. Let's go with hydrochloric acid plus sodium hydroxide, and that will go to the salt, which would be sodium chloride plus H2O, and I think that is balanced just as it is. We don't need to change anything. So it doesn't matter which acid, which metal hydroxide, will get that similar form. We'll just get a different salt form in each case. Acid plus a carbonate, and I'm sure this is a reaction that you've seen. So let's go acid plus carbonate goes to salt plus water plus carbon dioxide. That's the gas that bubbles. So here, let's say we took some sulfuric acid plus some calcium carbonate, that's limestone, which is a very common rock, and that will form calcium sulfate. Calcium has a 2+, sulfate has a 2-, so that's balanced. Plus H2O plus CO2. Just checking the balance. 1 calcium, 1 calcium, 1 sulfur, 1 sulfur. 4 oxygen plus 3, 7, 7, 2 hydrogen, 2 hydrogen. So that should balance. And, well, a hydrogen carbonate really is a carbonate, but they put them separately in the statement, so we'll do them separately. If we go acid plus hydrogen carbonate, we will get salt plus water plus carbon dioxide. Now we'll show you something slightly different here. All before I've done full equations. Often we only want to do these as an ionic equation. So let's just, rather than having the whole acid here, let's just show that general form of the acid, which is a H+, something that can donate a hydrogen ion. And we're going to react this with, say, bicarb soda, sodium hydrogen carbonate. Now here, instead of getting a salt, this metal ion, we don't know what the part here is, but we're assuming it's a spectator ion. So rather than getting a salt here, we'll get the ion. We'll just get the sodium plus ion, because we haven't put in, if you like, the other half of the acid, plus water, plus carbon dioxide. If we just check the balance there, 1 sodium, 1 sodium, 2 hydrogens, 2 hydrogens, 1 carbon, 3 oxygens, 3 oxygens, so that balances. So if you like now, that's just, if you like, an ionic equation. We could have had the other part of the acid here, but it would have been aqueous on both sides. It would have just been a spectator ion. Have a look back on the ionic equations video, writing equations video, where we talk about ionic equations and ignoring spectator ions if you're not sure about what's happening there. Okay, this is barely reactions of acids and bases, but this is where it is in the subject outline. We don't talk about the strength of acids or the strength of bases, but in this case we're mainly worried about the strength of acids. This was covered actually quite well in that video that we did right at the start. the video, the TED Ed video I pointed to you right at the start. But the key thing is a strong acid is completely ionized. It releases all of its protons. A weak acid is only partly ionized. Only some of the protons are released. A concentrated acid contains a large amount of acid. Okay, a high mole per litre concentration, now that we've done concentration units. Dilute acid only contains a small amount of acid, a low mole per litre. And all of what I'm going to say here applies almost equally to bases, but we're only going to deal with acids. That's all that's covered in the subject outline. So I think firstly, hopefully if you look at these, the concentrated acid, these two here, or the two concentrated, acids here and here, you can see contain a lot more particles than the weak solutions here. So when we talk about something being concentrated or dilute, we're just talking about the number of acid particles present. When we're talking about strong and weak though, we're talking about how many are ionized. So for example, if we have a strong acid, let's do it above this side. When we put, for example, hydrochloric acid, which is a strong acid, into water, I'll write it with this form, basically all of the hydrochloric acid will break apart to give us hydrogen ions and chloride ions in solution. So very, very, very few will stay combined as a HCl. They will all basically break apart, so all of these hydrogen ions are available to be donated. So this reaction basically goes all the way over to this side. As opposed to, for example, a weak acid, and an example there would be acetic acid, CH3COOH. This is one of the few acids where the hydrogen that gets donated is written at the end. Usually the hydrogen in an acid is at the start of the formula. Just a little thing to confuse us all. But when this reaction happens, actually I'll write that slightly differently. And you'll see why I'm doing this in a moment. When we put that into water, basically some of it will break apart to give the acetate ion and the hydrogen ion, but most of it will stay connected. So if you look in the diagram here with the weak acid, see how the little blue dots, they represent the hydrogen ions? They're all still attached nearly to the acid. So that's all still nearly together. Only a few of them are releasing these blue dots here, the hydrogen ions. Most of the blue dots, if you like, aren't free, they aren't being released, they aren't ionized. Same here in the weak. Only one here I think is ionized, all these rest haven't. Whereas we look at our strong acids, all of them are ionized, all the blue dots have been set free, just about all of the hydrogen ions have been released. So, very important you understand that difference between a strong and a weak acid, and a concentrated and a dilute acid, and you realise that just because it's concentrated doesn't make it strong, or just because it's weak doesn't make it dilute. Concentrated dilute is about how many particles are present. Strong and weak is about how many hydrogen ions are released. Thank you.